This video is on arithmetic sequences as linear functions. To begin, there's several definitions associated with sequences, and you should pause the video and make sure that you get all of these written down carefully. I am going to go over them, and you should either decide to work through my descriptions first and then pause, or to pause now and then listen to the descriptions. First, a sequence is any set of numbers with a pattern. Every sequence can be defined as a function with a domain of counting numbers. These are the terms, the first term, the second term, the third term. And the range is the sequence itself. We'll look at examples of this in just a few minutes. An arithmetic sequence is a set of numbers with a common difference. In the example here, 1, 4, 7, 10, 13, and so on, you can see that each number is 3 more than the number before it. And so there's a common difference, because if you start at the 13, 13 minus 10 is 3, and 10 minus the term before it, 7, is also 3, and 7 minus the term before it is also 3, and so on. And so that's called a common difference. A common difference is the number you get when you subtract one term of a linear function or arithmetic sequence from the previous term. So the common difference is denoted as D in the formula. A term is any element of the sequence. We call it n, which stands for the term number. And this n is used in place of x in sequence formulas. And you'll see shortly that the formula for a sequence looks very much like slope-intercept form. In the case of arithmetic sequences, that is, which is the only kind we're going to focus on right now. In the example, a sub n is read that way. You can see that the n is a subscript, and so be careful not to write that in your notes so that it looks like the word an. This is a regular lowercase a and then a subscript with the letter n there. This means the nth term. So a sub 5 is actually denoting the 5th term, and a sub 7 would be the 7th term, and a sub 1 would be the 1st term. And that way you can denote any term number that you need to talk about. The word infinite means that it goes on forever. And you'll notice that many sequences use what's called an ellipsis, those 3 little dots that come after a comma. It tells you that the sequence keeps on going. And so this sequence in the example up here is an example of an infinite sequence. It goes on forever. Finite, be careful, without the in front, we don't say finite, we say finite, and that means that it has an end. So if you didn't see this ellipsis at the end, this might be a sequence of numbers that goes from 1 to 13 but stops at 13. Maybe there are only 5 terms in the sequence. Most of the sequences we'll look at are infinite. Let's look at what's called a recursive formula, some notation, and we'll take some notes here. You should put this formula in red here in your notes. This is called the recursive formula for an arithmetic sequence. I know this is a lot of new terminology, but hang in there, because a recursive formula really just is a fancy way of describing the pattern that is taking place in a particular sequence. You'll notice that we have a sub n, that stands for the nth term. So I have some term that I'm talking about. Some term that I'm talking about, and what I want to do is look for the pattern, which would be given here, and all I have to do is plug that pattern in. It's the common difference. D is the common difference. It's the pattern. Now, this confuses a lot of students because I have an a sub n here and an a sub n minus 1 there. Let's take a look at this sequence. If I wanted to look at this term as a sub n, the next term in the sequence would be this one, right? And so if I was using n instead of a plain n, wouldn't I use the next one in the line, which would be, let's see, if this was the third term, this would be the fourth term. What would I have to do to the 3 to make it a 4? This would be a sub n plus 1. It's the next one, the one that comes after a sub n. What if I wanted to work backwards? What would be the term before a sub n? Well, this is the third term, so the one before it would be the second term. What would I do to n to get from 3 to 2? Wouldn't I subtract 1? And so the a sub n minus 1 is the term before some term, and the a sub n plus 1 is the term after some term. It's just saying go to the next one after n here and go to the one before n here by taking away 1 from the n. Be careful, these subnumbers don't do anything to the term itself. It just tells you whether to go backwards or forwards. And so what this is saying is some term is equal to the term before it plus the common difference, whatever the pattern is. So let's take a look at this. Let me erase my notes here. What's the first term in this sequence? All right, I hope you said it's the 4. So that's a sub 1, the first term. And the second term is the 7. A sub 2 is the second term. And the third term, a sub 3. All right, and so I could name any term this way. The 40th term would be a sub 40. If you look at this, 16 minus 13 is 3. 13 minus 10 is 3. 10 minus 7 is 3. My pattern, my common difference is plus 3, because when I'm moving forwards, I'm adding 3 to get to the next one and the next one and the next one. And so we write our recursive formula by copying the whole first part of the formula. A sub n equals a sub n minus 1. Some term is equal to the term before it plus 3. And so that's it. That's all there is to it. It's the notation that scares a lot of students. But this part doesn't change. Some term is equal to the term before it plus 3. Here's a term. It's equal to the term before it, 10 plus 3. And 10 plus 3 is 13. And 13 plus 3 is 16, the next term. And so you can just keep moving that way. Remember, in our notes, a sequence is a function. The domain is the counting numbers, and the range is the sequence itself. So in this case, the domain would be 1, 2, 3, 4, 5, 6, and so on, because there's an ellipsis that says this is an infinite sequence. The range is actually this sequence. 4, 7, 10, 13, 16, and so on is the range. So if you had to graph this, you'd use the counting numbers for your x's, your domain, every time, and you'd use the sequence itself, the terms in the sequence. 4, 7, 10, 13, 16 is your range, your y's. And then you would be able to plot the points and graph the sequence if you needed to. There's one more formula, and that is called an explicit formula. And this is the explicit formula. You should write it down. This is the explicit formula for this arithmetic sequence. And you'll be able to see that this is very much related to a linear function. So when we look at this, pick it apart, we have some term, a sub n is the nth term, is equal to a sub 1 means the first term, and we already discussed that n is the term number. And so up here, I give you the information that n is in place of the x. And so this will stay n unless you're figuring out what some term number is. And we'll do that in a minute. And then this is in parentheses followed by multiplied by d. Remember, d is the pattern, the common difference. And so all of that is here if you want to write it down and make sure that you know what each piece of this formula means. Let's use the same sequence and take a look at what the explicit formula is when we fill it in for this particular sequence. Let's try it. All right, a sub n, this is like my y, and a sub 1 is the first term. So I look at my sequence. What is the first term? I hope that you all said that it's a 4. That's the first term in the sequence. Plus, I don't know what term number I'm looking for yet. I'm going to be asking you to find the 30th term in a minute. And then that's in parentheses, and then I just have to put d in there. And d is the pattern, the common difference, and we found that that was 3. All right, well, anytime you see parentheses here, you can distribute the common difference to everything in the parentheses to make this look sort of nicer. Now sometimes they'll leave it just the way it is, but let's go ahead and distribute that. 3 times n is 3n, and 3 times negative 1 is negative 3. And now I have some like terms that I can combine, and I hope that you notice that when I combine those, I get something that looks very much like a linear function. This, if a sub n was just my y and regular n here was my x, y equals mx plus b. An arithmetic formula, an explicit formula for an arithmetic sequence is just a way of writing a linear function. So we can use this to find any term number, because if n is the term number, all we have to do is make n 30. And so that will give us the 30th term is equal to 3 times 30, because n is 30, plus 1. And when I multiply this, I get 90 plus 1. The 30th term in this sequence, 30th term, a sub 30, is equal to 91. And you could check it if you kept on going until you got to the 30th term, adding 3, adding 3, adding 3, adding 3, you'd get 91. So this is sort of a shortcut. You've got to get used to the algebra involved. But you can see how this formula actually turns into something that looks very much like what you're used to as a linear function. All right, that was a lot of information in a short period of time. Be sure to copy down the summary, as that's the highlights of everything I've touched on. Recursion, a recursive formula, just a fancy way of giving the pattern. It can only be used to describe consecutive terms. We use an explicit formula to describe an arithmetic sequence when we want it to look just like any other linear function. As long as you know the first term and the pattern, the explicit formula is very useful. I give you some notes on domain and range and a review of the notation here. We'll practice this more together.